Good evening, everyone, and welcome back to our CAWASA Wednesday webinars. This is webinar number 13 of the 2022 series. Our topic this evening is going to be the use of permeable reactive barriers for passive nitrate removal from on-site wastewater effluents. And our presenter is, our guest this evening is a registered professional engineer in both Alberta and British Columbia. Currently, she is the past president and current member of the WCOWMA on-site wastewater management of British Columbia, where she promotes implementation of environmentally sound practices within the on-site wastewater sector. With her environmental engineering background, she has applied her hydrogeological expertise to projects involving environmental risk evaluation related to groundwater migration. Project area include designing and completing monitoring for community water supply systems and landfill sites, groundwater supply evaluations, mine site water balances, on-site wastewater system design, aquifer characterization, soil transport analysis, groundwater at risk containing pathogens assessments, and source water protection planning, facilitating groundwater licensing applications and liaison between regulators and clients further rounds out her core practice areas. I have much pleasure in welcoming our guest presenter today, Ms. Bryer Manwell, a professional engineer with a Master of Science degree in Hydrogeological Engineering and president of the WCOWMA British Columbia. Welcome.
Thanks so much. Yeah, it's good to be here. I was invited by Valerie to provide this presentation, and this is a presentation that I've put together for the Virginia Mega Conference, the Mega Wastewater Conference that happens in Virginia each year. And so I've provided this presentation there as well as at the WCOWMA BC conference in 2020. So without further ado, I will share my screen and we can get going. There, that is not the presentation. There you go. Okay.
All right, thank you.
You've got that, and so I'm just gonna, there we go. So that gives some of the information that we've already spoken about. I'll just get right into it. So the overview of this presentation, I'm just going to speak a bit about who I am. That bio gives a pretty good introduction to me and my career. I'm going to speak about why do we need permeable reactive barriers, how I came about getting involved in the design and the use of permeable reactive barriers with respect to the on-site wastewater industry. I'll speak to you about nitrates and pathogenic bacteria that are the result of on-site wastewater disposal, and give a brief history of permeable reactive barriers and groundwater remediation. I'm going to discuss adding permeable reactive barriers to on-site wastewater designs, effluent quality, the longevity of the permeable reactive barriers, and then I'll take any questions. So this is me, and as mentioned, I have about 20 years of experience in environmental engineering, and most of that has been here in Western Canada, as well as a little bit in the United States. I think I'll be doing a little bit more work in the United States as we move forward. People seem to be interested in this rather highly sophisticated, low-tech method of and passive treatment of nitrates and pathogens. So it's, people are interested. Yeah, I do consulting work in all aspects of hydrogeology, so both water supply and wastewater. And let's get into this. So just to discuss a brief history of permeable reactive barriers. So what is a permeable reactive barrier? It's a passive treatment for groundwater contamination. And the first large field scale permeable reactive barrier experimentation was done in Baseborden in Ontario, Canada, by the University of Waterloo. And that was Gilman and O'Hannessy who studied the barriers and were able to put some data to that. So as you can see in this diagram, whether the contaminant source is from on-site wastewater, agricultural, even industrial waste, you can see that the contaminant can enter in from the surface. It can then migrate down into the saturated zone or the groundwater zone and form a plume. And that plume can migrate for some distance in the groundwater. The idea of a permeable reactive barrier is that you would essentially dig up and put in place an engineered material that groundwater could then migrate through, such that by the time it gets on the other side of it, it's been treated, or it's been passively treated to reduce nitrates, are what I've focused on. And the reason I focused on nitrates is because it's an issue in the on-site wastewater industry for when we install even type 2 systems. So advanced treatment units tend to have higher levels of nitrate from their effluent. And so, in these areas here like this, these are some shots or pictures from Okanagan Lake. I tried to make this presentation quite picture heavy. I live in a really beautiful part of the world and just wanted to capture that. So yeah, when we're dealing with on-site wastewater in the vicinity of both high groundwater tables as well as surface water bodies, whether it be the ocean or lakes or rivers or streams, those are sensitive environments, and nitrate can contaminate those surface water bodies, both from human health perspective as well as aquatic life. 3 milligrams per liter, I'll get into it in a little bit here, but 3 milligrams per liter of nitrate is considered above the chronic aquatic water guideline limit. So that's not a lot when we think about the levels of nitrate that can be coming from these advanced treatment units. Can be, upwards of 30 to 50 milligrams per liter. So why do we need them? Again, to protect the environment and human health. And again, just a couple more pictures of some work that I've done out on Okanagan Lake, which is where I'm joining you from. I'm joining you from Kelowna, British Columbia. So this picture just on the lower left-hand side, you can see that algal growth forming. And really that algae, the periphyton and chlorophyll A, are a result of the input of nutrients close to the surface water bodies, and they can become a nuisance. And again, when we start talking about nitrate specifically in these areas, these shorelines are very important to fish spawning habitat, and nitrate concentrations above that 3 milligram per liter can impact that fish spawning area. So along with those sensitive ecosystems, we're also trying to protect groundwater from nitrate contamination. And so this, for example, is a wellhead. And yeah, there have been many instances where operation of on-site wastewater systems have contaminated full aquifers, so drinking water aquifers. And it's a very difficult thing to mitigate once that contamination has occurred. So the idea is, well, let's not contaminate in the first place. Let's put the treatment in, the required treatment in, so that these aquifers can stay clean. So again, I'm just showing you a few more pictures here of this, this algal growth that you see down gradient of these systems that are producing nitrate and migrating into, in this case, this is the Pacific Ocean at Galiano Island. So quantifying contaminants. So land use water quality assessments show on-site is impacting the foreshore, or can, and nutrients, both nitrate and phosphates, as well as pathogenic bacteria, load the environment from these on-site wastewater systems, as I mentioned, near lakes and rivers and wells. And as I mentioned as well, that 3 milligram per liter, which is a fairly low concentration of nitrate, is considered our aquatic life standard. And if we're above that, we're doing harm or damage to aquatic life. For us in British Columbia, and I think it's a pretty universal standard, is the 10 milligrams per liter is the drinking water standard for nitrate. And yeah, often, or there have been instances where I have measured nitrate concentrations above that 10 milligrams per liter in aquifers that are affected by on-site wastewater contamination. So the way that I've been addressing the engineered material is within the design or the construction of the seepage field or the drain field. So I've been engineering materials to be able to essentially add a carbon source so that we're able to do the nitrate reduction. We basically make an assumption, but it's a sort of a found assumption based on sampling, that the form of nitrogen that is coming out of an advanced wastewater treatment plant or septic tank is going to predominantly be as nitrate, as opposed to nitrite, ammonia, or total congealed nitrogen. So this permeable reactive barrier works quite well in reducing the nitrate to negligible limits or negligible concentrations. So the materials, oh, here we go, that's fine. I'll go on to the next slide. Adding permeable reactive barriers to on-site designs. So this is an example of some hog fuel that is being added into a sand layer. Now, this isn't how this is going to look in the end. This hog fuel will be dug into the sand to make a permeable reactive barrier. So it's kind of a fancy word or fancy term, but in practice, it's quite pragmatic. And essentially, it involves adding a carbon source to either native materials or engineered materials for that seepage field. So again, this is the hog fuel that's been spread out over the area of where the drainage field or the seepage bed will go. And it's being dug in, so twist dug in. So this is about a 2.5 centimeter layer, sorry, 2.5 inch layer of hog fuel that will then be dug into about an 8-inch layer of sand, clean sand, and that forms the permeable reactive barrier. So here's another example of adding the PBR to wastewater designs. So again, I'm using hog fuel in this example, and you can see the observation ports. I've put in numerous observation ports underneath the seepage bed to be able to monitor the effectiveness. So we call it performance-based monitoring, and we can monitor the effectiveness of this permeable reactive barrier to treat these nitrates. So that's another example of addition of that technology to an on-site wastewater system design. And then in terms of monitoring, I've gone to using remote nitrate sensor monitoring or automated monitoring. So these systems that I get involved with tend to be in very sensitive areas, like I said, in and around surface water bodies. So to monitor or do performance-based monitoring and ensure that we are meeting our water quality objectives, I've been using this type of device, which is a automated nitrate monitoring device, which monitors the groundwater down gradient of on-site wastewater systems to ensure that operation is not causing harm to the environment or people, and that the system is operating as designed or expected. So this is just a table that's showing some of the examples of my use of permeable reactive barriers. So I've got a couple examples. One is at Christina Lake. And this shows you that in the groundwater down gradient of an on-site wastewater system, I had nitrates of over 10 milligrams per liter. And that was after installation of a new system. So that was after the redesign of an old system and implementation of a new type 2 system. And you can see that that system alone, without any sort of permeable reactive barrier, was not treating the nitrate to an adequate level, and was definitely loading at the shoreline above that 3 milligrams per liter. And then these other two examples are from the same location, And they show you the incoming nitrate concentration of the effluent. So I ranged from 3 milligrams per liter in July of 2017 to 32.5 milligrams per liter in May 2018. And at the end of treatment through the permeable reactive barriers, we can see that we end up in the groundwater with less than the detection limit, so less than 0.01 nitrate. So very effective. And then if we look at the E. coli, we can also see that we had 46,000 CFUs per 100 milliliters in the effluent, and then in what I'm calling the initial dilution zone, about 3.6, and then by the time we're into the groundwater zone, so after the effluent has migrated through the permeable reactive barrier, we're less than detection limits once again. So just essentially showing you the effectiveness of the treatment. So then in terms of, that's a question that I'm always asked, is the longevity of the permeable reactive barrier. This is again passive treatment. So the intention is that this is installed and then it stays in operation for the given length of time. Now this is a peer-reviewed article that has studied a permeable reactive barrier septic system design in Nova Scotia for over 15 years, and has found that the technology has maintained its applicability and hasn't found any major reduction in nitrate reduction over time. So essentially we're looking that these systems can last from 15 to 20 years and this would be with the assumption that the permeable reactive barrier is being installed within the VADOS zone, so the unsaturated zone. I don't expect the permeable reactive barrier to last as long if it is installed in a saturated zone. I think that you'd end up potentially having to replace it sooner because of the biological breakdown. So just a side note on that. This study assumes that the PRB is installed in a VADOS or unsaturated zone. But yeah, it's what I've used as justification to say, no, we don't think that you're not going to have to be taking this out and redoing it every 5 years. This is a technology that should be lasting 15 to 20. So just as a summary, on-site wastewater systems operated at the foreshore can cause nitrate plumes into surface water bodies, and that can cause pollution. Nitrate removal should be incorporated into wastewater systems design where there are sensitive receptors, so that being shallow groundwater and surface water bodies. So my summary is that you should use these permeable reactive barriers for treatment of nitrate. It's very inexpensive. It's very inexpensive both for installation, so initial costs, and then operating costs are also very low, again, because it's passive. There isn't ongoing maintenance costs. And yep, it's a low cost, low maintenance, long-term solution to help passively remediate effluent high in nitrate. And we suggest doing performance-based monitoring so that you can prove that the system performance is what you expected it to be. And that's it, pretty short. I can definitely take questions, and I'm sure we can get into
Sure.
Yeah, whatever
Thank
you've
you.
got for me. Yeah, no problem.
Colleagues, you're listening on, will you have any questions? I think for the benefit of many of us, I had just looked up the word hog fuel, but I understood it's a form of mulch, isn't it?
It's like a mulch. So hog fuel is sawdust would be a finer version, and then bark mulch would be like a more thick version, or just a more coarse version. The hog fuel is kind of that in between. It's like Goldilocks, right? It's the just right. So the sawdust is too fine, the bark mulch is too coarse, but the hog fuel offers us that sort of that perfect blend of, or that perfect surface area. Now, as I mentioned, there are other sources for carbon that you can use, zeolites, even coconut husks. There's many different, and I think, given your local scenario or what you have available, that would determine what you're using as your carbon source. Because again, I believe this technology is applicable in really anywhere in the world, as long as you have a, a locally available carbon source, which is typical, but yeah.
Yeah, colleagues, any other questions you may have, feel free. The floor is yours. Well, I noticed that it has been, well, you said it's on surface water and in shallow areas. Excuse me. Excuse me. So that if and this where do you apply it? Is it on the shore, or you would have to
No.
create some mechanism within the water system?
No, so it's actually here. Let me go back to I'll go back to my slideshow. Oh, hold on a sec. I guess I have to share my screen again. Let's do that. Share screen. There we go. And back here. Right. It goes here. Yeah, so you can see here, this is where we're implementing the engineered material, is
Right.
within the dispersal area itself.
Ah.
So again, here, so this is a, you know, the this is where we're actually going to be putting above this is put some they're called Elgin geotextile sand filtration system. Yeah, so that'll go above this. So again, you could put this into the water table itself. However, in the way that I'm applying this for wastewater design systems, this is going the addition of the carbon source and the creation of the permeable reactive barrier is occurring within the VADOS, or the unsaturated zone, and specifically it's being incorporated into the wastewater design, like the septic system design, the dispersal field.
Okay.
Does that make sense?
Yes, yes. And
Okay.
so then if we are, let's say, considering a constructed wetland, per se, that would be
Yes,
something that can be applied.
absolutely. So one of the, and I didn't show it specifically here, but one of my systems, and that's actually from the data set that I show. Go to this data set. This is a horizontal subsurface horizontal flow constructed wetlands. Excuse me, for Mara Lake. Yeah. So this is a system that's treating 35 homes, and it comes from an advanced treatment unit that does have nitrate reduction in it. But again, you can see that, you know, even coming out of this plant that has nitrate reduction, we're still seeing, you know, 32.5 milligrams per liter. So I think what's happening here is that these systems are operated in the summertime, and it takes a little while for the microbial population to even you know, come up to speed. And so I think that they're using it for such an infrequent amount of time that their advanced treatment unit really doesn't get the opportunity to get up and running. So what I've implemented there are 7 what I call polishing cells, and those polishing cells are themselves the constructed wetlands. So they're engineered wetlands, like I said, they are subsurface wetlands. So all of the flow remains subsurface.
Okay. There's a question in the chat, which reads, what's the average lifespan for the PRB?
So that would be, yeah, between 15 to 20 years.
Any other questions, colleagues? Feel free, comments. Well, there's silence, so I imagine we have no questions.
That's okay.
Yeah, but yes, go ahead.
Oh no, I just hope you enjoyed the presentation. I hope it was useful.
Yes, in fact, because, well, just some matters that we're dealing with currently, and I think it just triggered some ideas. So I think, yeah, that's a good one, which I will also share with some other colleagues who are onto that project. Yeah. So, well, thank you very much. I'd like to thank Valerie, who always finds for us some very good presenters, and across a diverse field of technical personnel. And this evening is no different. And we'd like to thank you very much, Bryer, for giving us that time. And of course, this is recorded, so we are going to share it on our YouTube page with our colleagues who may have missed it for one reason or another. And we look forward at some time in the future that we may have you again on maybe some similar topic or another that you may wish to share with us.
Oh, that sounds great.
Yeah, so thank you again very much for joining us, and wish you a pleasant rest of the day, and to keep safe and well, everyone.
Okay, thanks so very much. Take care.
So I'm Ignatius Jean signing off from
Okay.
our CAWASA Wednesday webinar series, number 13 of the 2022 series. Bye.